So we have fairly impressive evidence that some form of matter that interacts very weakly with electromagnetic radiation and exceeds the visible mass in the stars and all the galaxies exists. But what is it? So far, astronomers have only been able to play the game of elimination, ruling things out. We can think of a detective mystery where in the final scene all the possible killers in the stately home are gathered together, and one by one their alibis are inspected and they're ruled out of deliberation, and we find out who the final culprit was. Well, the game doesn't work that neatly in science. We may not be able to think of all the possibilities, but the number that have been ruled out is actually quite impressive. Let's start at the high end. What about black holes? Black holes, of course, by definition are black, if they're truly isolated in space. Perhaps the universe and galaxies are riddled with black holes, and that's the dark matter. That's actually very easy to rule out. Imagine that there was a party in your house, teenagers left alone over the weekend. You may not have been there for the party, but you'll sure see the damage they left behind. Well, anytime a black hole forms, there was a party beforehand in the form of a supernova, a violent explosion, ejecting gas, causing high energy emission, emitting X-rays in a supernova remnant for millennia afterwards. So it's impossible to form black holes without seeing evidence of the violence that preceded them as a massive star dies. And to have enough black holes in the universe to account for dark matter, you'd have to have vast numbers of massive stars dying at some point through history. We see no evidence of that. So stellar mass black holes are actually the easiest things to rule out for dark matter. The next possibility is interesting. Recall that as you go down the mass spectrum of collapsing gas clouds, there's a mass corresponding to 8% of the mass of the Sun, below which a star does not form. The gas cloud simply becomes hot, but never hot enough for fusion to occur. Nature will probably collapse gas clouds that are less than that number. They may be 5% the mass of the Sun, 1%, 0.1%. And so, in theory, there's a set of collapsed objects out there that are warm, but not radiating by fusion. And if they're small, they might actually be quite dark and not visible in light. These have been called massive compact halo objects. If the halo of our galaxy was filled with them, they could account for the dark matter. We already have an indication that there are many more low-mass stars than high-mass stars. So it's reasonable to hypothesize an extremely large number of substellar objects, ranging down to Jupiters and even below, existing in free space. Think of them as free-floating planets, if you like. This is harder to rule out, but lensing, the effect where mass bends light, has actually done so. Experiments in the mid to late 1980s looked for gravitational lensing taking place throughout the halo of our galaxy in terms of the momentary amplification of the light of a background star from a foreground star. That same amplification could occur if the foreground object was a massive compact halo object, a substellar object or a Jupiter, for example. The statistics of that search were very impressive, and they easily ruled out the halo being composed primarily of such objects. Machos, as they're called, may exist, but they don't form the majority of the dark matter. With normal stars, such as red dwarfs, and the remnants of massive stars ruled out, and also substellar objects, the last possibility is even smaller physical objects, say asteroid size, ranging down to house size or even down to dust grain size. In the interstellar medium and in the space between planets, there are of course a lot of rocks, and those rocks only emit infrared radiation. Perhaps space is filled with such dust or particles. It turns out this was ruled out 20 or 25 years ago by the IRAS satellite of NASA, which looked across the sky at far infrared wavelengths. Even if you hypothesize that space is filled with tiny particles or boulders or house-sized objects or asteroids, those objects do not exist in isolation from radiation. They're radiated by the light from nearby stars or galaxies, and they reach an equilibrium temperature sufficient to pump out infrared radiation. IRAS was a sensitive mission that would have seen the diffuse dim glow of far infrared radiation from such hypothetical objects. They simply don't exist. Also, that large an amount of dust in interstellar space would dim and redden the light of distant galaxies in a way that we simply don't observe. If we summarize this, astronomers have essentially ruled out dark objects ranging from black holes down to dust grains 1 micron in size. All that's left is the only current viable explanation for dark matter, a subatomic particle. So we're left with one viable explanation in physics or astrophysics for dark matter, a subatomic and fundamental particle. Remember the constraints. This particle has to dominate the number of normal particles. protons, neutrons, and electrons by a factor of several, so it's a ubiquitous particle. It has to interact very weakly with electromagnetic radiation, which puts a strong constraint on the type of particle it might be. In general, these particles are called weakly interacting massive particles, WIMPs, the acronym. We think that that's what the dark matter is, but no such particle has yet been detected, although searches are underway. What kind of particle might this be, even in principle? Physicists are aware that the standard model of particle physics is incomplete. One of the favorite extensions of the standard model of particle physics is called supersymmetry, where the fermions, particles with half-integer spin, and bosons, particles with integer spin, which have quite different properties in the laboratory, are actually unified in a sense by a range of shadow particles for each of them. This of course doubles the number of particles, because each fermion has a supersymmetric twin and each boson has a supersymmetric twin. For these to be unobservable currently, these would have to be high mass particles only available at very high energies, perhaps beyond our current accelerators. So this is speculative theorizing that unifies physics in an interesting way, but produces effects that are difficult to observe in the laboratory. It turns out that high-energy physicists, such as at the Large Hadron Collider at CERN, are actively looking for the lightest supersymmetric particles. And the lightest of them, or the least massive of them, could indeed have the properties such as to be dark matter. This is an exciting convergence between a desire of physics to explain physics beyond the standard model, and astronomers to explain one of their biggest enigmas. Unfortunately, supersymmetry is not one theory, it's a suite of theories. And with very little experimental guidance, it's been hard to discriminate between these theories. The slightly disappointing news from CERN in the last year or so is that hints of supersymmetry have not been seen in the LHC running at its highest energies. And this has already ruled out some of the simplest and most attractive supersymmetry theories. So although supersymmetry is desired by physicists and would provide a neat potential explanation of dark matter for astronomers, there's no verification of this theory at present. Dark matter remains an enigma. High-energy physics is trying to find supersymmetric particles by high-energy collisions, but there are other ways to find dark matter. So there's another set of lab experiments designed specifically to detect a weakly interacting massive particle, or WIMP. Most of these are situated deep down mine shafts because the major contaminating noise for any search for dark matter particles is interactions of cosmic ray with the detector. The detectors in these cases are usually large, ultra-pure lumps of solid-state material such as silicon or germanium. A series of these experiments is underway where the shielded detector, shielded from cosmic rays and other interfering particles, is simply observed carefully for a long period of time for the very occasional interaction of the detector particles with a passing dark matter particle. The weak interaction strength of the dark matter particle means that a large mass of detector, ultra pure, has to be observed essentially for years to find sufficient interactions. Current experiments are in a regime where in 3 to 5 years they should detect dark matter particles if they are indeed weakly interacting massive particles, the kind predicted by supersymmetry. At the moment it's tantalizing. No detections have been made, and within a couple of years, if the detectors still find nothing, then we'll be back to square one. Most of the supersymmetric theories, or plausible explanations of dark matter from particle physics, will have been ruled out. As for what dark matter is, so far we've eliminated everything from black holes down to small dust grains in space. The only remaining viable option is a subatomic fundamental particle, as yet unobserved in the physics lab or with accelerators, and representing an extension to the standard model of particle physics. The answer may be within a couple of years based on lab and accelerator experiments as to whether this dark matter particle actually exists.